That's good. And I can hear you as well, so that's very good. So the speaker is going to be William Kalderon. He's going to talk about fast pattern recognition for the Atlas track triggers at the high luminosity LHC. And you have 25 minutes, and you can start if you want.
Okay, great. So yeah, thanks for coming on to the recording. So I guess, as you all know, Atlas, right, is a large general purpose LHC experiment, and I include this picture mainly because it links to some fun reading material, so I'd recommend. And really, because it's a general purpose experiment, it does lots of searches and measurements. To keep pushing the research program, it needs an ever increasing flow of data. Leaving the data collection rate constant would render each year less and less useful statistically, of course. And so what this prompted is this high luminosity LHC campaign, which is going to be the program by which there'll be a large increase in instantaneous luminosity. So very many more proton-proton collisions per second. So you can see this on the diagram on the top right. So where we finished up the end of the last data taking was around 2 × 10⁻³ in instantaneous luminosity. That will stay not dissimilar for the upcoming run 3, but then the HL-LHC starts in run 4, where this number gets much, much higher. Now, of course, by keeping the bunch spacing the same, but desiring a higher luminosity, that means we need more collisions per bunch crossing. And so pileup, which peaked at around 70 in run 2, and that was quite taxing for the run 2 system, both in terms of triggering and the reconstruction. Run 4 might start at around double that, at about 140, and it will increase to around 200, so triple the run 2 value. And so to cope with this, Atlas and the DCMS, both experiments are going to have, well, they'll need much more capable tracking hardware. So the entire inner detector of Atlas is being replaced with a new inner tracker in order to really be able to tease out the vertices that we care about from the 199 others. So now that we can reconstruct events offline, of course we need to record them in the first place, because this huge collision rate is only useful. You have no efficiency to events you don't record. And so also, as well as upgrading the detector hardware, there are lots of upgrades in the works to trigger systems, as detailed in this TDR. And what we're going to end up with is, much as we have now, a multi-stage system where progressively we take more and more detailed information, and each step has more time to make its decision. So we start from the 40 megahertz input rate, and then there's a first level called level 0, which is colored in kind of purpley color in this picture on the right. And that makes very quick decisions at a 10 microsecond latency, and it puts out, it filters that down, that 40 megahertz down to 1 megahertz, which it passes to the event filter down the bottom, which takes that 1 megahertz down to 10 kilohertz that's sent to permanent storage. But it's really key that that 10 kilohertz is the most is really the 10 kilohertz that we actually want, and the most useful 10 kilohertz. And as part of doing that, tracking is absolutely essential for the performance of the system. Tracking is really key for things like particle flow identification, where you mix track and calorimeter information to really get a better handle on what your objects are in your event. It's very handy for instance, soft term and missing transverse momentum, also for jet tagging, so for B jets or quark gluon discrimination, for WZ Higgs top versus QCD enlarger, for tau, so on and so on. And this picture on the right is a little list of some of the physics goals of the HL-LHC and Atlas, and correspondingly which ones of them need tracking in the trigger. And so you see the ones that point down at blue boxes in the bottom is every single one of these physics cases benefits from some amount of tracking in the trigger, and quite a lot of them benefit from really full detector tracking in the trigger. So tracking in the trigger is very, very important to everything that Atlas wants to do. Well, almost everything. But the problem with this is that the trigger system has a fixed amount of time in which to make its decision, and a fixed amount of computing power with which to do so. So any tracking that is done has to be done very fast. And I suppose the other way of saying that is that the slower that the tracking is, the more limited it has to be. So limitations can be doing tracking only at a higher PT, or with reduced regions in eta or Z or D0. And so obviously we want to avoid limitations as far as possible. So the baseline Atlas plan is something called the hardware track trigger, which does high quality and fast tracking with associative memory, and it does this in kind of two setups. It has a regional part that can do this in level 0 regions of interest, and there are two different scenarios, but broadly they do them at slightly different rates. One of them looks for tracks above 2 GV, one above 4 GV, and then there's doing full tracks for the whole detector with G global HTT, looking for tracks at 1 GV. I say that just because those numbers will come up later. And as well as this, Atlas has also been looking into some alternative approaches, such as full software tracking or hybrid architectures with CPUs and FPGAs or GPUs. Now, this talk is going to talk about two fairly simple algorithms to seed some of this tracking, which are amenable to running on FPGAs, but it's not particularly contingent on any particular architecture or any place within that architecture. And very importantly, the proposed architectures are not particularly contingent to what I'll talk about. So this is the context in which it'll run. But given that that's still that's all work in progress, so this can slot in several places within it. So the first of these things is something called the Hopf transform. It's an image processing technique has been used quite widely for a long time outside of particle physics to find circles. And what it does is it maps each hit to all circles through that point and the origin. So if I look at this red point here, there are several different circles that I can choose that go through those 2 points, and they can be characterized by the initial trajectory of the circle and the curvature of the circle. And if I'm talking about a circle that has quite a high curvature, quite a low curvature, a high PT track, the relation between them is roughly a straight line. And so if I plot, I get something that looks like the bottom of the top right, so that red point maps to that red line. And if I then think about what it means to have these red lines intersect, that will mean that there are lots of points that all map at that point to the same circle, which is what's happening on this green line. So I have that red point, but then I have 3 other points that are all sitting on that circle. And so what that means is that if I identify the intersection, I have found a candidate track. So then the business is to find these intersections, and that's done by turning it into a histogram filling problem. So the lines are each plonked onto a 2D histogram, and then from that you just look at the number of bin, the bin maxima in your 2D histogram, and then some playing around with some parameters like the number of bins that you choose and what your maximum criteria are, and so on. Then you find the maximum and therefore your track parameter. Now, obviously, if you have, we've reduced the dimensionality a bit, so to thin out this the density of these histograms and therefore make the maximum identifier a bit more accurately, you can split this into multiple eta regions, as I show on the bottom, right? So you only consider, you split it into chunks in order to not overload this accumulated histogram and pick up false positives from tracks that couldn't possibly be near each other. Not hits that couldn't possibly be near each other because they're completely different places in eta. But so when we've done this, what you get is an initial set of track parameters and the hits that seed them, and they can then be used to seed precision tracking downstream. Now, however, there are some limitations on this. So the method is really designed for circles from known fixed origin. So in the case I've shown here, we have these 3 red hits that are coming from a displaced vertex, and you wouldn't find a circle from the origin that goes through them all. So this is also shown on the plots, especially the one in the middle, where as the true D0 increases, the efficiency decreases rather a lot. But you can tune the parameters a bit to to mitigate this impact. So this is what the one on the right is. It's showing with a certain amount of tuning, especially at high PT, you can recover some of the efficiency. The full treatment, however, it's possible, but it needs a more complicated transform on pairs of hits, which is much more intensive and much slower, and therefore less suited to trigger applications. But if there are various tunings you can do. But if we do a tuning on some ITK simulation with Pilot 200, then you find a suitable number of hits about 97% of the time for 1 and 2 GV tracks. So it can be quite efficient for as long as you focus tightly on the origin. A second method is something called stub finding, and this is where it's based on the principle that, of course, a lower PT track is going to go through the tracker layers at a higher inclination angle. So, right, if I look at the right-hand picture, there's orange is a high PT one that's going more straight. The blue one is coming at much more curved, and so that means if I zoom in on those layers and look at the kind of, these layers are all double layer, made up of 2 modules back to back, spaced by a few millimeters. Then the high PT drum will have only a very small shift in phi between those 2 layers, whereas the lower PT one at higher inclination will have a large shift. And so therefore I can reject hits that have a large spacing because they must have come from a low PT track. Now CMS implements this really with the design and readout of their phase 2 tracker, which I've shown a picture of at the bottom. They have, for some of the intermediate layers, these mixed pixel plus strip dual layers, which are particularly good at doing this. And that means they can actually build the stubs on detector. The stubs is these pair of hits. And once they do that and require a PT greater than 2 GV, they can reduce the total number of hits that they have to read out by about 90%. So that's quite a compelling number, and it's something we thought it would be interesting to look at for Atlas. So the Atlas phase 2 tracker is, of course, different. We only have strips, double strip layers. We don't have these mixed layers, and the pixel layers are just by themselves. And the stub finding is only really feasible in these thinly spaced double layers. But if we look at the bottom plot, how the occupancy varies over the strip detector, the channel occupancy is roughly 0.5 to 1% over really everywhere. And so if we combine this with the size of the strips, they're around 70 to 80 microns everywhere, then the delta phi between strips is on the order of, depending on, of course, the radius, around 0.1 to 0.2 milliradians. And so if we think, okay, 1% occupancy, I have to travel 100 strips, that means roughly we're on the order of 10 milliradians between hits. So that's quite a small number. It's obviously far too big to consider forming a stub from one layer to the next whole layer, several tens of centimeters away. But within the dual layers, it's feasible. So if we do some trigonometry to figure out what actually you expect to happen between these double layers, then I've plotted for the end caps on the right and the barrel on the bottom the kind of numbers you expect. So for 1 GV tracks, which are the blue lines on these plots, then the delta phi between these dual layers is about 2 milliradians in the barrel, and depending on where you are on the end cap, between 0.2 and 1 milliradians in the end cap. And that's to be compared with this number from the pilot box of the order of 10 milliradians. So that initially seems quite promising, but they're much smaller, and you see the variation with PT is roughly linear, certainly in the barrel. But actually, that's not quite the whole story, because there's a reason these modules come in pairs, and that's, of course, they're at a stereo angle, about 3 degrees between them, as that allows you to get some position information along strip direction. But that's obviously a very useful aspect of these modules, but it means that if I'm trying to work out the delta phi between hits in these 2 layers, it's smeared out by the fact that they're tilted. So this is why the CMS strip plus pixel modules are good at the stub finding, because they don't need to have a stereo angle. Now the size of this effect you can of course work out. I've drawn a little picture of the kind of 2-scale tilt and width of these modules. So you can see this is one of the short strips in the barrel. So you can see you do cross a number of, the uncertainty is multiple strips widths. It varies, of course, from the very, if you go through the middle of a strip, there's no uncertainty. If you go through the end, it's maximum. So on average, it's half that. But the average values are on the order of 0.7 milliradians for the barrel and 0.5 for the end caps. And so we fold these two things together and we get a kind of expected distribution. It looks like here. And the top plot is for 1 GV tracks and the bottom one is for 0.5 GV tracks. And you see, even with the smearing from the stereo angle, there is a pretty decent discrimination between the two of them. It varies according to which layer you're in, because of course the impact of the stereo is different with the different lengths of strips and the different radii they're at. But you can see by eye the actual. You can reject quite a lot of the low PT tracks while still accepting a lot of the high PT ones. Now these are slightly simplistic assumptions went in. The real world is a bit more complicated by the fact that, of course, by how the modules are stacked, and at the corners of the modules where they don't quite overlap, it gets a bit more complicated. And that accounts for about 2.5% of the module area is more complex. And so there will be smearing on the order of that many fractions of hits. The end caps have a slightly more complex shape. The distributions in the end cap have a more complex shape. But even here, we do still retain some discrimination between tracks of 0.5 and 1 GV. It's maybe a little bit less than we had in the previous one, but there's less that is missed out from the assumptions written here. So then what we observe, sadly I can't show you pictures of what we observe, I can just tell you a number. In simulation we see fairly similar distributions to what I said in terms of shape and the shifts thanks to the tilts that we see in the modules and so on. But there is a little bit of extra smearing. It comes out that if we require a 98% efficiency for 1 GV hit pairs, then we reject on the order of 20 to 30% of the lower PT ones. Of course, there's more rejection at 2 GV, but obviously less than same as 90%, thanks to the less optimal dissector layout. So this does look fairly promising, but of course studies are ongoing to translate this hit pair efficiency into a track efficiency, because that's really what we care about. There are a few subtleties, such as obviously not every track leaves 2 hits in a sublayer. It can be between 1 and 4 even, thanks to overlapping modules in the barrel. And we also want to evaluate the speed up in the downstream algorithms. So of course, thanks to combinatorics, it might well not be linear with rejection factor. And also, you could think of combining these two methods. So this stub finding could be used to cut down the number of hits that we pass to a Hopf transform, which would mean that you could expand the Hopf transform to higher impact parameters while keeping it feasible to run. So in summary, the HL-LHC is going to see significant upgrades to the LHC machine to provide many, many more protein removal collisions a second. This can only fully be exploited by upgraded detectors, data acquisition and trigger systems. And a key part of this, of having a performant trigger system, is to include track information as early as possible in the trigger decision process and with as few restrictions as possible. And I presented two methods to do some preliminary steps of track finding, a Hopf transform and stub finding. They're both fairly promising, but further studies needed to really come up with the full cost and utility of both of those methods. So thank you. Any questions?
Yeah, thanks very much. It was a nice talk, very interesting. This talk is open for question. Please raise your hand if you want. You mentioned at the beginning that this is an alternative to the baseline. I mean, it's in terms of FPGA hardware. I mean, do you require some dedicated cards? Because I mean, our level 1 system, our level 0 system is FPGAs in principle as well. Did you?
So certainly, we have some very preliminary look at the The stub finding is very resource light because it's really doing it depends quite a lot on what FPGA you have and how much memory it has going spare, because the actual amount of computation is very little, but you need to know where each strip is and to work out what you're doing. So it does slightly depend on that, but in principle, it is something that could be slotted in already existing FPGAs. The half transform, it requires, because it has to build this big accumulator, that requires more resources. But so that would require dedicated
cards.
Dedicated
Okay.
cards, yeah.
Okay, interesting. Are there other questions? Doesn't seem to be the case. Thanks very much, Will.